So we're going to start with our first kind of neat concept or applicable concept, which is line integrals. So we're going to consider two different types of line integrals. The first is going to have a physical application that essentially is going to find an area of something specific. And then the second is going to be a line integral within a vector field. And that's going to have an application to essentially find work. So before we do the vector fields, we're going to talk about over just a simple curve. So I'm going to start by kind of giving you the idea of what this is, and then we'll talk about actually calculating it. So we're going to let C be a smooth curve that is defined by the function R of t, which has whatever components x of t, y of t. And this curve is traced out between some values, let's say a and b. Okay. The other thing I want to make sure is I don't want to be in that case of like the unit circle. I don't want to keep going around my curve over and over again. So between these values of a and b, I want to make sure this is a smooth curve that is traversed only once as t goes from A to B. Okay. Now what's going to happen is I'm going to have some surface in 3 dimensions. This curve, however, is just in the xy plane. So it's doing whatever here. But now I've got some surface that's lying above it with the curve doing whatever underneath in the xy plane. So we're going to let that be defined by a function f. Let this be a positive and continuous function. Now what I want to do is, because if you think of this R of t, it's giving you a bunch of different xy coordinates for that curve. I want to make sure all of those xy coordinates can be plugged into this function. So I want it to be positive and continuous and defined on the curve C. So that basically means every single one of these xy endpoints of this vector can be plugged into this function to get a z value as an output. So let's get a little bit of a picture as to what's going on. So here is our 3D surface. So x, y, z. Okay. Then I have my curve here in the xy plane. Okay. So this is my curve C, and it's defined by the function R of t. And then maybe you trace it out this way. Orientation doesn't matter for this particular piece. Then I've got this surface defined by f. So maybe my surface looks like this, because it's always easy to draw. So here is z, which is a function of x and y. So all of these xy points here can be plugged into my function to get a z value. So I get maybe the z value up here. This would give me, I'm going to make that dotted to show it's underneath the z value here. Basically, every single one of these points can be plugged in, and you can get an image of that on this curve. But because it's curving, it could be that, there's some bumps up and down. It doesn't have to necessarily have the same shape. Okay. So this is what this curve looks like on the function. So if I plug in every single one of these values, you get the output, which is on the surface. What I want to do is I want to figure out what is then the area of this resulting shape. Okay. So basically, it's like if I look at the curve on the surface and then I drop a sheet down, what area is this curtain? Okay. And this is exactly what this line integral is going to calculate. So I'm going to show you where the pieces come from because we do the same thing. We basically break this into a bunch of smaller pieces that are more manageable. Okay. And then I'll take a zoom in maybe on this piece right here. Right. Now, when I have like a very small piece, it's not so curved at the bottom, but essentially we're going to break it down into smaller blocks. So this is that bottom piece right here, and then the rest is the top. Okay. So all I'm going to do is I'm going to take all of these typical elements and I'm going to go ahead and add them up. And so we're finding a bunch of areas of rectangles. The height of this is not so bad because that's exactly just the output of the function at whatever point within there. Now what we need is an approximation for this bottom length. And so in this case, because it's curving, we're going to use the arc length to evaluate that. So specifically, this will be the change in that arc length, remember, which is given by S and then ds, or delta S, which turns to ds. So the area of this typical element is going to be the function times the change in that arc length. Then we go ahead, we add all these up, we let the limit approach infinity, and so we know this is just going to become the inside of the integral. So this is exactly what a line integral does. It's finding the area of the surface along the line, aka the curve. So the line integral of f along the curve C is defined by you add them all up, so it becomes the limit as n goes to infinity of the sum from I equals 1 to n, and then the height is the function evaluated at whatever point in that interval. That point doesn't matter. And then that change in the arc length. So this turns into an integral. The function is on the inside. You're integrating with respect to the arc length, and that's the thing that's hard, over this curve C. Okay. So what I need to do is I need to figure out how do I actually evaluate this, because I don't know a nice way to integrate with respect to S. Because really you've got this curve that's defining everything here. So if you remember, you might have to go back in your notes, but when we talked about finding arc length of stuff, we actually calculated what ds was, or came up with another notation for it. Okay. But just in general, the area of the curtain that is below the surface Z which is that function of x and y, and above the curve C is defined by this line integral. Okay. So the line integral finds this total area here. You have your curve, you drop that sheet down to the xy plane, and it finds the curtain. Okay. So what we did before, way back long ago, was we talked about arc length. And what that was is when you had a 1 inside here as the function. So that gave us the arc length of some curve. The way we actually calculate that is way back in 13.3. we determined that ds is equal to the magnitude of r prime of t dt. So really, if I want to evaluate this line integral, instead I can turn it into a single integral involving t. We'd go from a to b since those are the bounds. Instead of x and y, you want to replace them by t, so you use that vector function because we're evaluating f at r. And then ds turns into r prime of t dt in magnitude. Okay? So these pieces have to be replaced by t because, again, we're looking at the curve on the function. We're evaluating it at r. So in general, if your function on the inside, oh, that should be if, is just 1, then this line integral is really just evaluating the arc length. Okay. So it's really an extension of this arc length formula to then have more complicated figures up here. All right. So really, a lot of these next couple sections are all going to be about doing line integrals. So I'm only going to do one for now, or two for now, and then we'll do a vector field one. Because the next couple sections, we're going to keep doing these things over and over. So we'll get lots of practice within that. So let's start with one we do not actually need to do this line integral for, because once we draw the picture, we can really just use a nice geometric formula. So let's evaluate the line integral along the curve C of the square root of 1 minus x squared minus y squared ds, where C is defined by r of t equals t 0, for t being between -1 and +1. Okay. So what I need to do is, again, turn this completely over into t. So I've got to do a couple things first. The function that I'm working with is the square root function. And then r of t is t0. First thing I'm going to do is I'm going to see what does the curve look like just along the function. So this means in my x component, I'm going to put the x piece from here, and in my y component, I put the y piece from r. So again, in place of x, I'm going to use t, and in place of y, I'm going to use 0. Because these are the same from here, and these are the same from here. Okay? So this is equal to 1 minus x squared minus y squared. So the function just along that curve is 1 minus t squared. The other thing I need to do is I need to find the magnitude of the derivative. The derivative is the vector 1, 0. So the magnitude of this is you do 1 squared plus 0 squared under a square root, and that's just 1. So I have everything I need then to evaluate this line integral. So we're integrating with respect to t. So my t bounds are -1 to 1. this first piece, 1 minus x squared minus y squared, turns into 1 minus t squared. And then ds has to turn into r prime of t dt. And so filling in what that is, this is negative 1 to 1, square root of 1 minus t squared, and then that really becomes 1 dt. Okay. All right. So this is actually a trig sub problem from Galc 2. I told you we aren't going to do a ton of these, but this is a really nice example, which is why I picked it, because this shape is really going to be a semicircle. So I kind of went back on my rule, but it's again just purely for this example to show you that this is doing exactly what I said it's doing. So if I want to go ahead and integrate this, I don't have a t on the outside, so I can't make a u substitution. If I want to go ahead and get rid of this square root, I've got to replace t by something, and in this case we replace it by sine of theta, okay? Because that will give me 1 minus sine squared, which condenses to cosine squared. And then here dt is then cosine of theta d theta. I also in no way, shape, or form want to have to go back to t at the end. So I'm going to go ahead and change over the limits immediately. Starting with t equals 1, or t, we'll do the bottom limit first, t equals negative 1. This would mean that sine of theta has to equal negative 1. And the only way that happens is because of the arc cosine. This will be negative pi over 2, because you only want that bottom half of the unit circle. When t equals positive 1, then that would be sine of theta equals 1, so theta will equal pi over 2. So I want those smooth swoops. I don't want to use theta as 3 pi over 2 because that doesn't give me that right half of the unit circle nicely. So plugging in each of these pieces, my new bounds are negative pi over 2 to positive pi over 2. That gives us 1 minus sine squared of theta. dt is cosine of theta d theta. And then 1 minus sine squared becomes cosine squared. And we're taking a square root of that. Technically, it gives you those absolute values, but because of the interval that we're on, the right half of the unit circle, it's positive there. So this is the integral from negative pi over 2 to pi over 2 of cosine squared of theta. The square root cancels, and you get cosine times cosine, so cosine squared. Maybe you remember how to evaluate this. You have to use an identity. I'll put that off to the side if you need, but cosine squared of theta is 1/2 1 plus cosine of 2 theta. So we can bring that 1/2 to the outside. This is negative pi over 2 to pi over 2. And then we're integrating 1 plus cosine of 2 theta. Okay. And now we're all good. We can take the antiderivative. That's theta. That's going to be 1/2 sine of 2 theta, evaluated from negative pi over 2 to positive pi over 2. And plugging in our values, the upper bound gives you pi over 2 plus 1/2 sine. When you times that by 2, you get sine of pi. And then we subtract negative pi over 2 plus 1/2 sine of negative pi. And thankfully, both of those are 0, so they do not matter. And that really gives you 1/2. And then you get pi over 2 plus pi over 2, which leads you to pi. So you really get pi over 2 as your answer. Okay? So the area of this curtain is pi over 2. But again, what I want to do, the reason I picked this particular problem is to show you because we can graph all of these components. So the function that we're working with, z, which is 1 minus x squared minus y squared under square root, this is the top half of a sphere. Of radius 1. Okay. And then our vector function r of t is again t0, where t is between -1 and +1. So if I go ahead and graph what's going on here, make sure we draw all of those back pieces. Let's make sure they're dotted. Then we got a circle of radius 1, so 1, -1, -1's back here, +1 here, and then +1 up here. So again, just the top half of a sphere, so draw it down, and then draw it this way. And then we've got the circle in the xy plane that looks like this. Okay. Now if you go ahead and draw this curve, if you notice it's just the x value, we do not move in the y. And then my x ranges between -1 and +1. So this is really just tracing out the x-axis. This is our curve C. So if I look at my function specifically on this curve C, all it's doing is taking that xz trace. Okay? That is the image of the curve along the function. So the curtain that we're finding is really what is happening in the xz plane. Okay. And it is just a semicircle there, because all you would do is you let y equal 0 and you get that circle of radius 1. And then here is that curve C at the bottom. Okay. So we are finding this area. But we know how to do that because we know what the area of a circle is. So the area of this curtain is pi times the radius squared, and because it's a semicircle, it's over 2. So you get exactly pi over 2. All right. So this is indeed exactly what this line integral is doing. I'll do another problem where the actual integral isn't as bad. Like I said, trig substitution is not something that's going to pop up very frequently at all. Not something I would give you on a test either, but homework, at least then you can review it if a question like this comes back up. Instead, we'll look at a different example that I'm not going to be able to actually draw the picture for, but we can still go through the process of finding this line integral. So for our second example on this, we're going to evaluate the integral over the curve C of the cube root of xy ds, where C is the curve y equals x squared, where x is between 0 and 1. So the problem with this one is they don't give me a vector function r of t. Instead, they just tell me what the curve is. So I have to go ahead and parameterize this curve. Okay. So to guarantee I'm on the parabola, we're going to let r of t be the function where my x is t, which means your y has to be x squared, so t squared. And since x is just being replaced by t, my t is varying between 0 and 1. Okay. So this guarantees I'm on that curve. So now we have our vector function. We need to go ahead and find a couple things. We're set to go ahead and find this magnitude. So let's go ahead and take the derivative. That gives me 1 and then 2t. The magnitude of this is then 1 squared plus 2t squared under square root. So that is 1 plus 4t squared under the square root. My function is the cube root of xy. So when I evaluate this on the curve, my x gets replaced by t, and my y gets replaced by t squared. And so that really gives us the cube root of t cubed. So luckily this simplifies to just t. Okay. So I have everything I need to actually evaluate this line integral. We need to first evaluate the function on the curve. Well, that becomes t, because we did that. And then r prime of t dt is 1 plus 4t squared under square root. And our t is varying between 0 and 1. So again, just to separate these pieces for you, this turned into t. This is the function evaluated on the curve. And then the ds turns into this piece here, because this is the magnitude of r prime of t dt. Okay? All right. So we are all set. We now have this as a single variable integral, just to clean it up so I don't have all of these colors and words above it. We're really evaluating this integral. So this is a much nicer one than the last one, because this one I can indeed make a u sub 4. We can let that be 1 plus 4t squared. So du becomes 8t dt. I don't have the 8, but that's not a problem. Just bring it over, and the t dt will get sucked into that du. I again want to change the limits. This is not something anymore, especially when we're about to get to double integrals and surface integrals. You've got to switch your limits over. When t equals 0, my u is equal to 1 plus 0 squared. When t equals 1, u is equal to 1 plus 4. So my upper limit becomes 5. So switching everything over, I'm getting the 1/8 from the du. My new bounds are 1 to 5. And this becomes root u du. And then you can change that over too. I'm not going to make a new integral for that. That's u to the 1/2. So bumping that power up gives me 3/2. Dividing by 3/2 is the same thing as multiplying by 2/3. And then we evaluate this from 1 to 5. And then we can clean this up a little bit. 2 over 8 simplifies to 1/4. So this becomes 1/12. Then we get 5 to the 3/2 minus 1 to the 3/2. And that is the area under this curve along y equals x squared. Okay? So like I said, we'll do a ton more examples where in the next section we're going to have to parameterize different segments, especially if you have like two pieces to a curve, like maybe it's a straight line and then an arc. You might have to do multiple line integrals. So give your homework a try, but if you need to go ahead and look at the next video first, absolutely. Instead, what I'm going to do is going to talk about what is a line integral in a vector field. And so this is that concept where I talked about your vector fields can represent like force fields. They can be like fluid fields. If you're walking in like a wind chamber and there's wind vectors pointing in all of these directions, well, what does that represent then? Or how do I figure out the work that I would need to do to walk along a specific path? And that's what these line integrals are going to calculate. So our last thing is a definition and an example. So we're going to let F be a continuous vector field defined on a smooth curve C. Given by some function R of t, where t varies between the values a and b. Then the line integral of the function f on C is defined by this is representing the work. So if you remember how to do work, or if you've ever looked it up, or if you're taking physics, it's usually going to be the force times the displacement. So in this case, our force is given by that vector field. And then the displacement's a little bit harder. So in this case, because we're working with vectors, instead of multiplication, we use dot product. And the way we're going to kind of discuss the displacement is going to deal with that tangent vector. So it's going to be the force dot product with that unit tangent vector, ds. Okay. So it's still going to depend on that change in that arc length along that curve. So the tangent vector kind of tells you the direction you're heading, but it's going to be how we can calculate that displacement. What this really is then is TDS is just dr. Okay. So ultimately, all I'm going to do, these are way easier in general, is you're going to take F, you're going to dot product it with R prime of t, and then integrate with respect to t. But again, F is going to have to be evaluated along that curve. So all of your X's, Y's, Z's, whatever it is, has to be replaced by the components of R of t. Okay. So just add that in here. This F is really defined on that curve again. So we're seeing what does the force field look like? What do those vectors look like on the curve? So break it down one more time. This is really the force dot product with the displacement to calculate the work that you would do to move through that vector field. So let's try an example. We are going to evaluate the line integral of f dot dr, where f is going to be a triple xyz, and it's going to be given by x squared e to the xy, x e to the xy, and then e to the z. And the curve C is the oriented curve defined by R of t equals t squared, t cubed, for t being between 0 and 1. Oriented just means it's traced out in one direction, as the direction does matter. If you think about the work, if you walk forward and then walk backwards in a different direction, well, then you're doing opposite work, because in one direction maybe the wind is pushing you, so you're not doing anything, but then when you're walking against it, it's the opposite. Okay. So we've got our vector function r of t. We need to do a couple things. I do not need to find the magnitude, which is very nice here, because again, I'm just going to dot product it with f, but I do need to find the derivative of this. So we've got t squared, t cubed. We need to find r prime of t, which thankfully is nice, 1, 2t, 3t squared. Next thing I need to do is I need to turn this vector field f over in terms of t. So I'm going to evaluate this along r of t. So my x gets replaced by t, my y gets replaced by t squared, and my z by t cubed. So my first component, x, is t, and then xy is t times t squared. So this is t squared e to the t times t squared. Second piece, that's x, so that's t. And then we've got e to the x times y. Last component is e to the z, and z is t cubed. So this is e to the t cubed. Okay. Now you absolutely can jump into taking the integral at this point, but just to kind of clear things up, I like to personally go ahead and find the dot product between these two things, because that's what I'm going to end up integrating over. So I'm going to take t squared e to the t cubed, t e to the t cubed, e to the t cubed, and dot product it with 1, 2t, and 3t squared. So when I do the dot product, I just multiply those like components and add them together. So this gives me 1 times t squared e to the t cubed. Then moving on to the second component, t e to the t cubed times 2t gives us 2t squared e to the t cubed. And then last but not least, e to the t cubed times 3t squared gives us 3t squared e to the t cubed. And thankfully these are all the same thing, so I have 1 plus 2 plus 3 of them. We have 6t squared e to the t cubed. So this is going to be what we integrate over. So the line integral of f dot dr is just the integral from 0 to 1 of our vector field along our curve, dot product with r prime of t dt. So we're really integrating from 0 to 1 of 6t squared e to the t cubed dt. So this, just a u-sub problem, will let u equal t to the third. So du is 3t squared dt. And you can separate the 6 so it has the 3, but you can also just move the 1/3 over and then do the division with the fractions. Okay, so let's go ahead and change our limits as well. When t is equal to 0, u is equal to t cubed, so thankfully that doesn't change. And then this is really nice because when t equals 1, u is 1 to the third. The limits get to stay exactly the same. So this is great because I don't have to do any work to go back. So the 6 times the 1/3 is going to leave me with a 2. So this is the integral from 0 to 1 of e to the u du with a 2 out front. And then the antiderivative of e to the u is e to the u, evaluated from 0 to 1. So that's 2e to the first minus 2e to the 0. And so the work that you would do to walk along this particular path in this vector field would be equal to 2e minus 1. So again, we'll do way more examples in the next section, and we'll kind of see another extension because we're going to talk about that conservative vector field, and we're going to see how it's not going to matter about the path you take in a conservative vector field. And so we'll tie a couple loose ends together.